In this video, we are going to look at some of the basic operations for data encryptions, and later on for authentication algorithms we may use, and also we mentioned briefly in the previous video. So this is basic operations for data encryptions. Sorry. Oops. Okay. So as we said earlier, that these encryption operations need to be efficient, which can be implemented at the hardware level as well as at the software level. So the first operation is exclusive OR. Okay, so this is exclusive OR, and so it is a logical operation. It is the easiest. So this is a logical operation. Logic operation, I'm sorry. Let me put it, it's a logic operation, or sometimes we call it Boolean operation. Boolean, it's capital B. Boolean operation. So it has a simple rule. The input and out, they are all operated on bits. Okay, so this is on bits. So we have this is called truth table. We have input X, output X, and I'm sorry, input X and Y, output would be X exclusive or Y. So the rule is, if both are 0, it's 0. If one of them, exactly one of them is 1, then the output is 1. If both of them are 1, the output is 0. So this is a exclusive OR. Okay. The line here. Okay, so then this is equivalent to a modular 2 operation. So this is really, so X exclusive OR Y is equal to X plus Y modular 2, where X and Y are bits. Okay, so later for some algorithms where we're going to generalize this modular 2 operations to, okay, to, let's put a K here, to a exclusive OR K, and which of this operation would be X plus Y modular 2 to the K. Okay, where X and Y, our values belong to the range from 0 to the k minus 1. So where this means that the length, okay, so these are our binary with, so we can think of that these numbers are converted into binary format with the length X will be, let's say, equal to K. Okay, so these will be later on that we may need to use this generalized exclusive OR. So that means for this, the normal Boolean operation exclusive OR, we can think of it as X exclusive OR 1, because this 2 is equal to 2 to the 1's power. Okay, so that is the first operation that we know that we can simply use exclusive OR as encryption. Okay, and of course decryption. All right, so the idea then, let's do it over here. So the idea is that you have an input, let's say my plain text M, and which is a string such as this. And just write it down. So let's say 1 0 1 0 0 0 1. Okay, and then let's say my K. So this is M. My K is 0 1 0 1 1 1 1 0. So now I am going to apply this exclusive OR encryption. Okay, so first I know that this is 8 bits, okay, or 1 byte, or 1 byte. And now we divide this M into blocks. So this is the block 1, okay, or M1. Sometimes we call it M1. This will be M2. Okay, so this will be M2. So now when we go down to the next one, we don't have enough bytes. So that means now we need to pad. We do some padding by putting some extra bits so that now we can have a M3. So usually the padding we would like to use would be to use something that's not printable. Not print. All right, so not printable. So we could, assuming that your origin, for instance, in this case, since we only assume that we need to fill in 4 bits, so is not the same like an ASCII code. For 8-bit ASCII code, 8-bit ASCII code, so encoding, though they have something that's not printable, but for this, let's just assume our original message doesn't have repeating zeros for 4 times. So let's say this 0, 0, 0, 0, in our case, is not printable. So which means that it's not going to be in your plain text. So then we can just pad this. So then you will know that this is a padding bits. So encryption then would be exclusive OR. So directly exclusive OR. Okay, so which means that I'm going to apply this K on each data block. So now we have, so that means we're gonna have, in our case, 1, 1, 0, 0, 1, 0, 1, 1, that's the first block. 0, 1, 1, 1, 0, 1, 0, the second block. 0, 0, 0, 1, 0, 0, 0, 0, the third block. And then I'm going to apply my K. So this is M. Okay, so 0, 1, 0, 1, 1, 1, 1, 0 repeats here. 0, 1, 0, 1, 1, 1, 1, 0. Repeat this here. 0, 1, 0, 1, 1, 1. Okay, so I'm not lining this right. So, okay, so this 0, 1, 0, 1, 1, 1, 1, 0. So then you do a bitwise exclusive OR, you got C. So using our truth table, what we're getting 0, 0 is 0. 0, 1 is 1, 0, 1 is 1, 0, 1 is 1, 1, 1, 0, 0, 0, 0, 0, 1 is 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So this is 1, sorry. Sometimes you do it too quick. 1, 1, 0, 0, 1. So that's C. Okay, so decryption is C, or using, so decryption would be M, which is C exclusive OR K. So K is used for both encryption and decryptions. This is a semantic key encryption and decryption. They use the same key, so we can now we can see this. So let me put this one somewhere else so that I don't have to repeat this. So now I'm going to, so this encryption will be M is equal to C plus K. So now let's just look at these two. Okay, so we, when we do encryption, we do these pairwise exclusive OR on these two rows. Now so this is encryption. For decryption, we are going to use these 2 lines. So this is encryption. And these 2 lines will be decryption. Okay, so then we can see here. So 0, 0 is 0, 1, 1 is 0, 1, 1 is 0, 1, 1 is 0, 1, 0, 1, 0, 0, 0. And then this is 0, 1, 0, 1, 1, 0. Okay, now let me see whether I line it up right. 0, 0. Okay. So it looks like I have one more 0 here. So, yeah, I'm right. Okay, so this is for here, and this. So this 1, 0 is 1, 0, 0 is 0. Okay, now let's see. Where do I do that? So this. Oh, sorry. This and that is the same. Okay, so we go this and that. So that is okay. 0, 1, not this. So it's 0, 1. So that you have to line up very well when you do hand. You can do it by hand. And then so 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1. So then this is my M. You can compare, right? So they are the same. And then this is padding. So you remove it. So this is to be padding. It's removed. Remove padding. Okay, so that is the basic operation. So we are going to use this a lot, but not alone, because we know that using k alone and k is repeating, then it is not secure. So we know it's not secure if k is reused. Okay, because k can be learned pretty easily using chosen plain text attack, or sometimes we call it non-plain text attack. So that would be very easy to break. So, but nevertheless, exclusive OR is convenient. It's simple. So it will be used a lot, but it will be used in addition. It will be used as part of the encryption. Okay, not alone. So also last time we mentioned if k is only used once, then we have this concept called one-time pad, where the sender and the receiver possess the same book of k. So each time they have to synchronize well, so that they know which k to use for encryption and decryption. So this is the safest way, but it is not practical for network communication. So the second operation is permutation. Okay, a permutation is we pre-compute a mapping, one-to-one mapping. So this is one-to-one and also on-to mapping. Okay, so you can think of it as a long table. Okay, so let's say you have a bit, A1, A2, A3, and so on. Let's say this is AN. And then this is your inputs. So this is the input. Okay, let's assume these are characters. Okay, let's say this is a byte level. So let's say this is a byte level substitution. Byte level substitutions. Then this is output. Would be then, let's say, the easiest one would be, let's say, is an minus 1, an minus 2, and then this is a1. So then if it's in English, will be A, B, C, right? So this will be the input up to Z, and then this will be Z, this will be A, so Y, X, right? So that's how you do a permutation. So this is a one permutation, but there are many different permutations. Altogether, you have n factorial, many different permutations. So you just need to choose one, and then that will be a table stored on your machine, on your program. And when you do encryption, you substitute each these character, for instance, substitute A with Z and so on. You store the same table. When you decryption, then you substitute Z with A, Y with B. So that is so permutation is also a encryption and decryption. But again, using this alone, it will keep the statistical structure of the original plain text. So which of course, by doing statistical analysis, by figuring out frequencies of letters, you can get this table. Okay, the attackers could compute this table itself by just looking at the ciphertext, compute letter frequencies for the ciphertext, and also compute, also get the letter frequencies of the underlying language. Okay, so again, it is easy because you can do it beforehand. So this would be your key, right? So this could be, then this is your secret key. Secret key. The algorithm is substitution. So you base on this particular key you chose, then you can do encryption. And this is also the same key, but you use it differently. Okay, so you use it differently. So that's a decryption. Okay, the other thing I would like to talk about here is that sometimes instead of writing a long table, we can write substitution into a two-dimensional table. Okay, so this is more convenient. So we write, this is 1D table into a 2D, two-dimensional table. Okay, so this then will be called a this will be called a matrix. Okay, so how can you do that? So so one way to do this is by looking at each byte. So we can break a byte, right? So we can break a byte into, so this is 8 bits. We can break it, say this is a 4-bit prefix, and this is a 4-bit suffix. And then what we are going to, for each byte, There are lots of different ways to substitute a value per mu, so we can just make up as a 4x4 matrix. I'm sorry, not 4x4, so 4-bit can represent 16 different values. So that will be 16 rows and 16 columns. Okay, so let me put an easier one so you can visualize better. Oops. Let's just look at a 4-bit. So let's say we got a 4-bit input. Okay, so then this will be 2-bit prefix, 2-bit suffix. So this way I get 4x4 bit level substitution. I'm sorry, 4-bit 4x4 4-bit substitution. So yeah, so this is a 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 0, 1, 1, 0, 1, 1. Okay, so for instance, I get a 1 byte. So altogether, you get 16 different cells. Okay, 4x4 is equal to 16 total different cells. And that if it's a permutation, each of these value has to be different. For instance, I can have, so this has to be 4-bit. So let me just, okay, for instance, 0, 0, I'm just going to go to 1. I'm just writing down something, okay? So this is a permutation. And this is all 0. As long as none of these will be the same, then it is permutation. Okay, so for instance, maybe I could have 0, 0, 0, 1 here. So as long as none of these cells in the matrix are different, none of these are the same, then it is a permutation. But then you can think of there are so many ways to rearrange these values. So now how you do a permutation now is just a table lookup instead of looking at linear. So when you have an input, you use the prefix 2 bits as your row number, the 2-bit suffix as your column number. And if your input is 0, 0, 0, 0, then you know you do this table lookup, you get the output is 1, 1, 1, 1. But then, of course, you can apply this differently. For instance, you can use the first 1 bit and the last 1 bit as the row number and the middle as a column number, right? So you can do that too. But nevertheless, permutation is a pre-computed table, either a linear form, in the linear form or in a binary form. And so none of these elements in this, either in this form or in this form are the same. So they are different. Then it is 1, 1 and on 2 mapping. So then we know it is a encryption and decryption, but it does not change statistical structure. So using it alone is not good enough. Hence, we would like to find a way to combine exclusive OR and permutation. However, using these two alone may still not be enough. So then we have the other operation called substitution. Okay, so substitution, so let me just put it here. Substitution can also be viewed as a pre-computed table, but some of these numbers, the output in this cell are the same. So they are no longer one-to-one, okay, no longer. So no longer one-to-one. And hence, of course, it's not going to be onto. So, so for instance, in this particular case, I can change, for instance, if I change this to 1, 1, 1, 1, then it is a substitution because this cell and that cell is the same. So when you look for 0, 0, 0, 0, you get output 0, 0, 0, 0. I'm sorry, you get output 1, 1, 1, 1. If you look at your input is 1, 1, 1, 1, you still gets the same thing again. So that means it's not reversible. So substitution is not reversible, and then substitution is not a encryption. So it is. So substitution alone cannot be used as encryption. So this cannot be used as encryption if it's not permutation. If it is not one-to-one, because that is not reversible, okay? So, but both of them are pre-computed. Permutation and substitution are pre-computed in the form of either a linear table or a binary table. Okay, so it is more often that we use binary table because this is convenient to write, and also we can apply matrix operations. And then we often use a circular shift, say. So this is a circular shift. We mention it because it is a form we would like to use. This operation can be easily done at the hardware level. Okay, efficient, but it is just a special case. Special case of permutation. Okay, and if it's just non-circular shift, then it is a special case of substitution. Those are easy to implement. So circular shift is like this. Say this is your 1 byte input. Let's say this is 1, 0, 1, 1, 0, 0, 1, 0. So if we do a circular shift to the left by 1 bit, then the output becomes, we shift to the left, so this is 1 going back here. And then we're going to copy the 0, 1, 0, 0, 1, 1, and then 0. So that is your output. Okay, so this is input, and this is output. So as you can see, it is just a permutation. So you can just keep doing it, okay, many times, okay. So sometimes you can do a circular shift by 2 bits, 3 bits, and so on. So if it's a non-circular shift, okay, if it's non-circular, then you get a substitution. So you do shift, let's say you do shift to the left by 1 bit, but it is not non-circular. So what you're getting then will be this 1 bit is out. So what I get, 0, 1, 1, 0, 0, 1, 0. Okay, so now, so then there is something here. It's not circular. By default, it will just be filled with 0. So it is. It is another operation. So the last operation that we would like to use is we have the arithmetic operations, all 4 of them, addition, subtraction, multiplication, and division on finite fields. Okay. First of all, fields would be, we have 2 operations, okay, plus and multiplication. So it's a plus and multiplication. So both of them has unit. So they share the same unit number and also inverse, okay? Share the same unit number and also has an inverse operation. So the plus, the inverse is minus. Addition, inverse is division. Okay, so for instance, and plus unit number. Plus unit for multiplication will be 1. For plus and minus will be 0. So it's a unit. So let me put it here. Unit. So this will be 0, will be 1. Okay, let me change this division to a more visible symbol. Oops. Let me use this division. But it is just actually inverse. Okay. I put an inverse over here. Inverse. And they also satisfy a set of rules of operation, like associative distribution rules. So for instance, the example will be all real numbers. It's all real numbers. They are few, okay? So it's all real numbers. But in our case, we don't want to deal with all real numbers because in a computer you can't you cannot represent all real numbers because what you can do is just an approximation. So we want finite fields instead. So we can define the same on finite fields as a finite number of numbers. Okay, so it's a finitely number of objects. You can call that as numbers. Okay, think of it as numbers. Those may not be numbers. And then I can define the same set of operations on these. If there are such operations you can define, then it is called a finite field. So, so the good thing about this, for instance, there was a French mathematician called Galois. I think this is how it is written. So he studied finite fields. So that now we can call it Galois field, GF. So if so here we want to make a connection to what we are going to use. So we are going to use either at a bit level, but when we use finite field operations, of course, we are no longer just looking at bit level because that bit level would be too trivial. So we're going to look at, for instance, look at the byte level operations. Byte level operations, and hopefully we get all of these arithmetic operations. So then the corresponding finite field is denoted as GF, so Galois field. So this mathematician Galois invented it. Okay, so then this is 2 to the 8. So that means for 2 to the 8 is 256. So for a finite field of 256 objects, you can define these operations so that it is, so you get addition, you get multiplication, you get inverse. For addition is minus, for multiplication is division, and then it has a unit. So for this plus and minus unit is 0, and for this is 1. So such things exist. And not only that, it has a good representation. So this could be represented. So each element in it can be represented by a polynomial. That is revolution in this field. So there's each number, each element, let's not call it number, right? Because it's object. Each element in this can be represented, uniquely represented. Oops, it has to be uniquely by a polynomial. So this polynomial of degree 7 with coefficients. Let's call it bit coefficients. So that means, for instance, if I have a byte, so let's call this byte A7, A6, A5, A4, A3, 2, 1, 0, where each of these AI is a bit, either 0 or 1. And so this is an element, okay? In this Galois field is an element. Then it can be uniquely represented by a polynomial. And this is A6, 5, 4, 3, 2, 1 plus A0. Okay, so the plus here is just exclusive OR. So now it has a multiplication, and inverse, the subtraction is also the same, exclusive OR. We already saw it, right? Because we know that so when we look at exclusive OR encryption and decryption, then we already know that the inverse of exclusive OR is exclusive OR itself, the operation, from the operation, right? But then we have to define multiplication. So that is just the multiplication of polynomials. But division needs, is not as trivial. So it needs something called irreducible polynomials. So those are the subjects that people study on finite fields. But for our purpose, we don't really need to understand a lot of details behind this. But what we just need to take is we'll take it as a granted when they told me division is done this way. Okay, so then we'll just take it as granted because now they have a strong mass to support that. Okay, so we are going to see these two operations when we talk about advanced data encryption standard. So AES standard. Oops. So advanced data or advanced encryption standard. So then we will talk about these. So that now I give, so with this video, I give you some ideas of these operations that we are going to use for devising a data encryption algorithm. They will be a combination of these two. I'm sorry, of these 5 operations. Okay, so of course, for simpler encryption, you don't need finite field operations. For AES, you do. Other than that, all these encryption algorithms are creative ways of defining these operations and creative way of combining them and using them.